Okay, so thank you everyone for joining the guest lecture, which will be delivered by the Songyou Peng, who is the research scientist at the Google DeepMind in the San Francisco. So I guess many of the people here might know his name with lots of his influential papers about the 3D reconstruction and the 3D analysis. And Songyou is also the recipient of the PhD award from the Computer Vision Association in 2024. And also he has received many kind of awards like Best Paper, the honorable mention at the 3DB 2024, and also the Best Presentation Award at the ICBSS 2023. And he received his PhD from the ETH Zurich and also from the Max Planck Institute in the 2023 under the supervision of the Mark Polyface and the Andreas Geiger. And also he's the author of the many interesting papers like Chaves Points, NiceSLAM, MonoSDF, OpenScene, and I guess Songyou might introduce also some of his work here. So Songyou will talk about I guess, Gaussian splitting and also about some other 3D reconstruction techniques. So please take it away.
Well, thank you. Thanks so much for the warm introduction. Yeah. Well, hi everyone. I'm Songyou, and it's a great honor to be able to give a talk here to you guys. It's actually and I just told Minghu that it's my first time giving this talk. I just prepared this talk. I don't know. I just finished preparing like half an hour ago, and so might not really work very well. Let's see. I will try my best. And actually, I will actually give a talk at Stanford in 2 days, and this will be the same talk. So, yes, just yeah. Okay, cool. Yeah. So the title of this talk is a Splatacular Year of 3D Reconstruction. I'm very happy with this title, but because it's actually the whole talk will be about Gaussian splatting, and like how we have already pushed forward 3D reconstruction with Gaussian splatting, basically. But to go a little bit backwards to motivate why 3D reconstruction and also, I don't know, the related topic is important, right? So imagine, I don't know, an intelligent system like, I don't know, autonomous driving cars, or like yourself inside the metaverse, or a home robot. Like maybe like, yeah, it's a more proper example in this case, right? Like roaming around inside this complex 3D environment. So to interact with the environment, the robot needs to perform like many complicated tasks. So there are like two like key components. Like the first key component is that you want to create a digital twin from this real world scene, so that like, you can interact with the world, right? So this requires like accurate geometry reasoning of the scene. And then like once you can do the 3D reconstruction, you can also really do something called like 3D scene understanding. So basically you can analyze the scene digitally. So this will enable the robot or machines to really interact intelligently with the scene. Okay, so both remain as like very active research area with many open questions. So basically this has been like my PhD was mainly about these two topics, like 3D reconstruction and 3D scene understanding with the deep learning methods. So I mean, like one big topic around my PhD was about like how do you reconstruct the complex 3D scenes. So I have like some works along this line. Basically, I try to reconstruct the large scale scenes. And on the other hand, we also work on a little bit on this like fast inference for the 3D reconstruction, for example, like the straight path points, and also like we speed up NERF, called a paper called Kilo NERF. And then another very important topic is that, well, you also should like be able to reconstruct from just like 2D observations, right? So imagine you have your cameras, and then you walk around the scene, and you just want to do the 3D reconstruction from only the 2D observations. And last, like once you get the 3D reconstruction out, you can do some high-level 3D scene understanding. Yeah, but so this basically is a very high-level summary of my PhD, and this talk will be focused only mainly in like 3D reconstruction, right? So my PhD thesis, what I just showed before, already tackled some challenges in 3D reconstruction, as I just mentioned, right? For example, how do you reconstruct at scale? That's like one of the main topics. How do you reconstruct at speed? And how do you reconstruct from like 2D observations? And so basically, I made these memes here. So what I have already tackled, and actually what's really remaining in the challenges have been remaining in 3D reconstruction. So it's really just like an iceberg I have already solved. There's so many more remaining there. In my opinion, like there's an ideal 3D reconstruction pipeline. So it's my personal opinion. We can discuss this, but we want to have a instant post-free real world 3D reconstruction everywhere. We can like robust like reconstruct everything everywhere. Yeah. And in order to achieve this, like the first thing I think is very important is that like, well, you want to have a model that is just like feed forward. So basically, you don't need to do the continuous like optimization, but like focus only on the like feed forward. So you can have a network or anything, like just like have one pass and get the 3D reconstruction out, and that's the goal. And then also we want, of course, like we want the camera pose. We don't want to assume that we have the camera pose given, right? So we want to have it like pose agnostic. And then also we want to handle the real world is like in dynamic, right? So we want it to be able to also handle dynamic. And then of course it's one of the very important aspect of like having 3D reconstruction is that like, you should be able to do very fast rendering or like real-time rendering. So this will enable so many applications ranging from, I don't know, games to many more. And then also like to robustly reconstruct, you should be able to also handle like arbitrary length of the scene. Like assume you have like 1,000 images or you have 2 images, or you should be able to handle them. And last but not the least, I think like it's normally like ignored, but actually also very important that it should be like lighting robust. For example, you have the images like under different lighting scenarios, you should be able to handle it as well. So okay, that's basically the 6 components in my opinion right now, except for like you should be able to reconstruct like large scale. You should be reconstruct like from 2D images. I mean, like, because like that's already sort of like tackled, right? So that's the current thing like still remaining to achieve an ideal 3D reconstruction pipeline. So Bill Gates, actually I remember this quote from Bill Gates is saying that like, well, people normally like overestimate what they can do in 1 year and underestimate what they can do in 10 years. I think like this this quote is like half true. So because I think people can really achieve a lot in 1 year. So the reason why I'm trying to say that is that like, well, I defended my thesis in November 2023, right? And I want to see that, hey, how much can I push forward the goal I mentioned above like, until November 2024, which is basically the deadline for CVPR, right? So like it's like 1 year time. Okay, how much can we push forward? But then before saying that, like we want to check, like, okay, so I graduated around like 2023, right? And then we want to see, okay, what actually came up in 2023. One thing is like very important thing what you guys probably already learn about from before is the 3D-GS, right? So basically, just to quickly recap, is like you give like some input images with the corresponding camera poses for each view, and then you pass it through like 3D-GS, and then you should be able to get such a real-time rendering for like high-quality scenes, right? So this is like a 3D-GS viewer. That's like one main thing in 2023 in the field of 3D reconstruction. There's another thing. It's basically called Duster. What Duster is doing is that I will give this kind of again unconstrained image collections. You pass it through this feed-forward network, and then the output from this network is the corresponding like point map for each image. So it's basically a 2D, 3D mapping, right? And what's very cool about this work is that like it leveraged like this very large network and then very big data training. So it will even like, so this is a very strong prior knowledge in the 3D world. So even if you give like these two images as input, which if you can notice, like there's no overlap at all between these two images, and it's still able to output something like that and like the 3D reconstruction, which is really, really cool. So they're like, well, we have 3D.js, which can enable a really fast rendering, and we have this Duster, which has like a very strong prior knowledge, and it's a feed-forward network, right? So just one pass, and then you get the 3D as output. So we come back to our like 3D reconstruction pipeline. So basically, the feed-forward part is like the Duster, and then the fast rendering part is 3D.js. So basically, can we first try to combine these two things and then to see what can we do? So this is basically something we call like feed-forward 3D Gaussian splatting, right? So basically, as you can see here, this is a large scenes actually, and this whole thing was done just in like by a feed-forward like single pass, and we output the 3D.js of the scene. So this is actually the first word I want to like talk about. It's called DepthSplat, right? So it's also accepted to CPPR, upcoming CPPR. And yeah, so the great work from Haofei. And so basically this work we try to do is that, well, first, maybe again, a little bit of motivation. So we have something called like PixelSplat or MBSplat, which is already some previous work to combine feed-forward Gaussian and Duster basically. However, there's some issues there. Is that like, well, it works very well, like it's multi-view consistent because it's trying to output the coherent 3D.js, right? However, it's really lack of robustness. For example, like for this kind of textureless region, many times will fail. And on the other hand, we also have some really strong prior knowledge, like again, like something called depth anything v2, which is like train a feed-forward network that try to give like a single image of any sort of image. You can get really high quality, crisp depth as output. And they are really robust to any sort of input images. However, because the depth itself is like they predict it's up to scale. So we have like the unknown scale and the shift, right? So naturally we were thinking, well, can these two things can benefit each other? Well, here is basically the pipeline that we want to try to combine these two things, right? So first, as you can see here, like, well, the pipeline is that giving the multi-view images with their poses, right? And we have a branch of like predicting the multi-view depth, basically. And then we have another branch, which is the monocular branch, which is basically we take the depth anything v2 as the like as a pre-training, and then we try to concatenate these two set of features. So basically now with the multi-view branch with like multi-view stereo, you can have like the multi-view consistent representation. And on the other hand, you have this monocular branch which will provide this additional robustness. And we concatenate these two features and then fuse them with a 2D UNet, and you can output the corresponding depth, which is consistent and then also very robust to different kind of input, right? And we can project the depth to 3D because you also know the intrinsic parameters, and you also know the camera poses in this case, right? And then you can like just unproject it and then to the 3D in the scene. And then you can now render this 3D Gaussian to some novel views, and then you can have the loss only on the RGB, basically. And what's cool here is that like, well, this part is actually something called unsupervised pre-training for depth, because it's like you don't actually need depth information at all, but you can actually backprop through this loss to update the prediction of depth. So we will show later that like this actually helps a lot on the depth. Well, that's like the pipeline. It's very simple, right? As you saw. So like one thing we can do is this feed-forward like view synthesis. So assume that you give these like 6 input views in a room, right? So you can see that actually they are like sort of like everywhere in the room. It's very sparse. And with the DepthSplat, you can get something like this, which is actually very cool. So it's actually for the first time. Well, there's some previous work can already do some sort of 3D reconstruction, but not really be able to like walk around like this and like in multiple rooms from just like 6 views. So it's actually the first time enable this. And another thing is that, well, we can increase like to 6 views to like 12 views. So if you do something like that, then that's actually the reconstruction even for like such large scale scenes, which again is very cool. And to just compare a little bit to some baseline methods, again, like compared to like PixelSplat and NVSplat, which is the previous state-of-the-art work. Well, state-of-the-art means that it was published in like CVPR 2024 and then ECCV 2024. So yeah, as you can see here, like we're giving this like 2 input, which is actually kind of far away from each other. Yeah, it's previous work, as I said, right? It was not very robust. So I actually suffer a lot to get like crisp detail. Yeah. Another thing like we want to show here is that what not just like giving like high quality novel synthesis, right? We actually also able to produce like better depth. For example, like NVSplat, you can also produce the depth, but as you can see here, right? So it's well, the depth is actually wrong, completely wrong in this part compared to ours. We actually produce this correctly. And so what we want to show that because the whole thing we try to do, as I said before, right? It's with RGB loss is unsupervised like depth pre-training, and we only did that like on the real estate 10K, and then we do this like pre-training, and then we try to do the supervised fine-tuning on the Titan Air and the like Virtual Kitty 2. It's a very standard setup. And here is actually a curve that we got. Is that like, well, this is the curve that without the 3D-GS pre-training for the depth, right, and the prediction. And here is the one with this additional pre-training with only RGB. And it helps actually a lot. So just like to quickly to recap the work, right? It's basically what we try to do is that we show that the depth and the Gaussian splatting are actually helping each other. And you can see that it's one of the first work that can do feed-forward Gaussian splatting for large-scale scenes. And like all we need is like a few pose images as input. Now the problem is that this is actually not a practical setting. Because like how can we actually get the camera poses from just like 2 camera views, right? Imagine like, well, we have like 2 views like this. Again, these 2 images has no overlapping with each other. How can we get the camera poses from these 2 views? It's actually not very trivial. Because there's like normally like when you get a camera poses, you need to know the correspondences across different views, right? But in this case, you don't even have the correspondences because it's like looking at different views. Yeah, so it's actually not a practical setting. So then like we want to see that, hey, well, this enable already like the feed-forward part and the fast rendering part, the DepthSplat already did that. So is it possible to further enable this pipeline for like pose-agnostic work, right? So again, the goal here becomes to, well, give these unposed images, like images without any camera poses. We hope we can have a method that is able to directly output the 3D Gaussians. And then you can also, from the Gaussian, you should be able to do the non-visual synthesis. So basically the same task, but without the camera poses. It sounds like, well, it's just remove the camera poses. Actually, it's not trivial how to achieve that. So basically, this comes to the work that actually just from last week, the iClear 2025 is called No Pose, No Problem, NoPoSplat. Basically, yeah. So basically, the work explore how to design a generalizable 3D Gaussian splats, right, from sparse and unposed images. It's very simple, but we will show that why it works. So again, to recap a little bit, this is a pipeline of the SOTA method, like a pixel splat, but you can also like relate it to DepthSplat or also the NVSplat and all this work, right? So the camera poses, as you can see here, they are used in like two different places. First, they are used in pixel splat. They are used for inject the epipolar geometry, and then in the NVSplat or DepthSplat, like the camera pose are used to construct the cost volume, right? So that's like a one place that is the camera is used. And actually, another place is that you have the camera poses, and when you have the Gaussian from each view, and you want to warp the Gaussian to the canonical frame using the camera poses, and then to this so-called like the Gaussian in the canonical space. So our goal here is try to remove the dependence of camera poses as input, right? So the first thing VIT, basically the backbone with the geometry prior, is easy to adjust, because instead of like incorporating this geometry prior knowledge, what we can do is that we just replace it to a standard VIT, easy. But then like the second part, basically do the warping. That's how to eliminate the reliance of camera pose to transform the local Gaussians into a global one. That's actually trickier to resolve it. Like what we do is that instead of predict that, we directly from the VIT directly predict the 3D Gaussians of all views in this canonical space. So this is not done just. We are not the first one doing this, right? Again, we look at the Duster. So back to this Duster paper that we mentioned at the very beginning, they demonstrate that like you can actually, given these two views here, you can directly produce or predict the point map in the canonical space without the need of like camera poses from two view. However, like does such a similar philosophy apply to Gaussians? Like this is an open questions, but this question is very important, because by predicting 3D Gaussian instead of point clouds, we actually have like several advantages. So if we compare this like point maps and the 3D GS, is that the point map is a discrete representation. You don't really get to really represent the scene with like very dense things like 3D GS that you can enable non-visual synthesis, so you can have like the beautiful images as output. The point map is just the points. Second, if we can just like train from the 3D GS, like you don't need to have the ground truth depth for the training. For example, like in Duster, actually train on like 15 or 20 data sets that each one has the depth as input. So if we can remove this need, then actually we enable the video, we just can train from video data. And we know that on YouTube, there's like billions of videos and it can use for training, and which is a great benefit. So here is like NoPoSplat is really simple. It's nothing else but the following. I just give a high-level overview first. So the first thing is to do is that what high-level doing is that, again, given the unposed image, you pass through this network, and then you can directly output the 3D Gaussians in the canonical space. And then you can use this, once you have these Gaussians, you can use it for like downstream tasks like, well, because you already have the Gaussians, you can estimate the camera poses for the input views. You can also do the novel synthesis. But going into the detail of the architecture, so again, it's very simple. What I do is I assume you have like 2 images as input, but this can be extended to like 3, 4, 5 views as well. I just use two images as example. You input each one of it into a VIT encoder, right? Just a standard VIT encoder. And then you can just decode and use the VIT decoder and with some cross attentions between views. And then like the decode thing will be directly outputting the Gaussian center head, which is basically the so-called point map, right? And then you can also like output using another head to output all the remaining Gaussian parameters. Here. And what you can do is that you can directly fuse these two together, so you don't need to do the warping as we said before. And that's basically the 3D Gaussians in canonical space. And then you can, again, do the novel synthesis. You can splat to a novel views, and then you can apply some loss on these novel views with L2 and L-pips. And so it's extremely simple. However, it doesn't work out of box like this. I wish it works like that, but there are like multiple issues. So this simple architecture, the first issue in this such simple architecture is that like we realize the output is getting very blurry. We found that this render novel views have really blur, especially on these like texture rich regions. And this is like caused by the VIT backbone's downsampling here, right? So you downsample and you upsample, and then you already lose some informations here. So what we do is a very simple fix. You can add a shortcut from the image, the input image, to that. Basically, directly connect the input images from input to these upsample features here in the DPT head. And this basically preserve the low level texture information. And then like there's another issue, is the scale ambiguity. So if you look at the projection equation, as you can see here, right? So it's basically a 2D. The pixel is you have like 3D points. You have the intrinsic parameter. You have the rotation and the translation matrix, and you use that to project to the 2D plane. But then there's an inherent ambiguity here. Like you can have like different intrinsic or like extrinsic, like different combinations that can lead to the same pixel. And that's an issue, right? So this leads to the so-called like the scale ambiguity, especially. So to solve this problem, we add basically this additional intrinsic embedding to the network. So for example, we assume that we know the intrinsic parameter. Actually, normally we know the intrinsic parameter is very easy to estimate it. So we can have the intrinsic parameter, we can encode them to the feature, and then we just concatenate them together with the image. And so this actually solves the ambiguity introduced by this projection process. The third issue is that once getting the canonical 3D GS in the space, like we can obtain the camera poses, right? But how do we get these very accurate camera poses? It's also not very straightforward to do that. Like one thing you can do is very straightforward, is that you have the Gaussian center, right, as the points, and you can directly ransack like PMP on this Gaussian center to get the coarse camera poses, but it's not very accurate. So like what we do is that you adding this additional refinement stage, and then you can further optimize again with the photometric loss. So it's back prop through the Gaussian, through the VIT, and then to get the camera pose basically. Yeah. So as you can see here, like once we have both PMP and the photometric loss, like the this AUC is like actually better. So to demonstrate the effectiveness of like this like canonical Gaussian prediction, so this like I show as you can see here, right? So compared to if you like do this local prediction and then do the warping and all that, like actually directly using this canonical Gaussian is predict in the canonical Gaussian space is actually giving you this high quality results, and you don't have this like ghosting artifacts. And second is that this image also shows, I don't know if you can see clearly, but like adding this image shortcut, you can list to like the sharper details, so that this texture blurring problem is solved. And then we also discussed this intrinsic embedding, right? So it's actually very important. And then as you can see here, without this intrinsic embedding, it's just quite, they have this scale ambiguity leads to wrong prediction. So that was just an ablation. So there are many more things we can discuss. So first, is some boring graph about like the pose estimation. So we evaluate on some like common benchmark, right? As you can see here, these two lines are the NoPoSplat, and especially the purple one is we jointly train on the RE10K and the DR2DV, and which not even like train on the ScanNet, right? And we can achieve actually the state-of-the-art results on relative pose estimation. It's worth noting that like the Roma, this blue column, they were trained on ScanNet, and then even that, like in our case, like we can outperform them in quite a significant way. It's very surprising. And another thing, like also NoPoSplat offers like the better geometry quality in the reconstruction Gaussian, as you can see here. So, well, that's the reconstructed Gaussian. This is the NVSplat, which even require camera poses. And if you look at here, well, we can reserve the geometry much better. And look at here. Yep. And another thing is like as a result, here, because we have this better 3D GS, as you can see here, right? So you also enable like even better appearance quality, especially when the image overlap become very small. For example, like the overlapping part is only like 5% or something, and our methods can actually beat all these like methods that require even camera poses. Yeah. Here's some rendering novel view rendering results compared to baseline methods like NVSplat. As you can see here, it's like it's definitely like without like those kind of ghosting effects. And then for this like out of domain generation, so for example, if we only train on the IE10K, which is only like indoor scenes, right? And then you can directly apply it to like the DTU, for example, as you can see here, it's like object level reconstruction, which means that it's actually generalized well. And again, like here's the results compared to, like if we directly apply to the ScanNet++, yeah. And further to show this like generalizability, so we also show this in the wild data, right? So as you can see here, the image extracted from Sora, this image from Sora, and just pass this into our pipeline, and looks well. This is like from the text and tempo. Again, input these two images, and then that's the rendering from output. There are some artifacts here, as you can see, but again, that's what we could get. Then here's another image that just taken by iPhone. these two images almost has no overlap, as you can see. The only overlap is just this here. So yeah, it's quite cool. Again, some take-home message. Well, the feed-forward like MVS can be surprisingly simple, as you see here, right? So the whole pipeline is basically a VIT, and then you output the Gaussian in the canonical space. Easy, with some small tricks, and then you can already make it work. So that's why in the title we say it's surprisingly simple. To me, it was very surprising. And as a side product, actually, this actually leads to like state-of-the-art relative pose estimation, which was also surprising. And we realized this works pretty well with like most of the static scenes we saw, thanks to this like strong prior knowledge from the feed-forward network, right? Again, it's more practical than like DepthSplat, but like it's still, I think, like not practical enough, right? Again, so I personally care a lot about whether the research can be like really useful for some of the cases, and for example, like I went to ICCV in 2023 in Paris, and then like I just like casually capture these videos, like expecting if we can like have a method that is able to reconstruct or render this magnificent architecture, this what's the name of it, like Arc de Triomphe, yeah. But then as you can see here, right, you have this bus is just completely like occlude the entire scene, and then you have like a moving cars, you have the moving humans in here. So how can we really reconstruct such a complete scene? And then you also have like such a long video, it's like arbitrarily long, right? How can we like handle that? So basically this inspire a line of other research that I was interested. It's basically, again, motivation is that like, well, is it possible to obtain this so-called like distractor free? The distractor is basically this moving dynamic object, and we can get the clean 3D reconstruction as output from this so-called like casually capture and long image sequence in the wild. So that's the goal. Again, back to this ideal pipeline that we want, right? So, well, in order to achieve what I just described, it's basically we want to handle dynamic, we want to have like arbitrary length, right? Let's like take other parts out first. Like these two are the things that we care a lot about. So how can we actually handle the dynamics, right? As we see that this bus was like passing all the time. And if we have a way to produce such a like uncertainty map to model the this dynamic part and also the humans here, and so if we can model this uncertainty, then we should be able to remove it also properly. So, but the key thing is that how can we actually learn or get such a good uncertainty map, right? Then enable us to remove it. Well, there's also this like a foundation model called Dino, right? So basically they can produce like universal features like this. As you can see here, well, this dog is like moving around. And as you can see, that's the feature actually with some thresholding. But it's very consistent across different views and like semantically very correct. And as you can see, like, well, the legs are always the same color, the head is always the same color. So this means that it can preserve the temporal spatial consistency, right? So is it possible to leverage this like Dino V2 to model uncertainty for the 3D reconstruction? So that's basically come to the work from last year's CVPR, right? Actually, these two, it's led by two master students. Wei Ning was doing his master thesis, Zhihan was doing his like semester project, and then we basically managed to get a nice paper out. The pipeline is as following. It's very simple. So giving the RGB image as input, and we pass it through Dino V2. So we extract some Dino feature map. And then we have, with the RGB input, you can train a nerve, right? So you have the nerve representation, and you can have the color from this like nerve representation. And then on the other hand, you have you can input the pixels of this like dino into some uncertainty map, and then output basically the uncertainty for each of the pixel, which is the alpha here. Wait, beta, sorry. And then what you can do is very simple. Is that to train this thing, you can have an SSIM and to model the structure, but then the loss will be actually conditioned on the uncertainty. So on the very uncertain part, the uncertainty, this beta will be high. So this loss will be actually this part will be almost like zero, right? So this will encourage during the rendering or during the training, you encourage not to look at the part there with like high loss, with high uncertainty. Yeah. So again, like to learn this uncertainty map, like we try to use some this like SSM loss. And why is that? Like, why do we want to use that? Because we can really leverage the structure information when the RGB color is very similar. Look at here. So this is basically, this is the training RGB image as an input, right? You have this weird toy here, which has like similar background as the as here. And if you just like calculate the RGB loss, actually you can see here the difference here will be very, very small. However, if you calculate the SSIM, you can clearly model this part. So we will just encourage it to focus more on the structure, not focus much on the RGB. So SSIM loss is actually just simply the sum of this luminance plus contrast plus the structure, right? So yeah, so we basically in the end consider using this SSIM, and it helps. So then the pipeline is just like this, and then once you use this like to train the uncertainty. So and then once you can train this uncertainty, at the same time you can use this to weight the RGB for the nerve training. And that's basically the pipeline. But there are like more details, but I won't go into them. But let me just quickly show some results. First, we capture a data set called on-the-go data set. So we have like cover from a low occlusion to medium to high. So the high one is actually not very realistic because it's really try to cover with like all sort of like weird things. But yeah, I want to show you, for example, in this case, it's the train station in Zurich. So here's the input images, and you can see that there's like some cars, some human, even the tram is passing through, the buses, etc. And here's our rendering for this part. And compared to the baseline method, like nerve on the wild, robust nerve, we can actually like model much better this static part. Yeah, and then we can remove, if you remember, we remove all the moving cars. And here is actually a very difficult case. Again, we want to reconstruct this gondola, but then most of the case actually we are covering it. And here is again, this is the results compared to the baseline method. It's like, yeah, I find it very interesting. You can actually, yeah, delete most part. I mean, it's not ideal, but that's the best we can do at that time. Yeah. So we also did some analysis. Basically, with our method, it's actually it's very efficient. So this is robustness of the baseline method. After even training for like 250K, the difference is it's not improving that much. Like this is the LPIPs, the lower the better. So like the LPIPs was like 0.35. And then in our case, like even after training just like for 25,000 iterations, it's already like lower than they're like trained for a very long time. And then even so, as you can see, you can make the training faster. Another thing is like, well, what if there's no moving objects at all? Can this work still? right? So as you can see here, yeah, robust nerf will remove like some of the static parts. But in our case, we actually still keep like all the structures. And it's like very similar to a completely static based method like the mid-nerf 360. So this means that our method can be even like dropping to replace the previous like nerf methods. So again, like this nerf on the go is a plug and play for all the nerf methods, and then we basically integrated it into the nerf studio. And we found the Dino V2 really rocks. It's really awesome. But there's some issues of the method, right? As we know, well, it's a nerf representation. It's really, really slow. So yeah. And also another issue is that in the wild, many of the images, they have, again, different like illuminations. As you can see here, this famous fountain in Rome. And yeah, so people are taking from different time, and with like also people like occlusions in the front, right? So can we also handle this case? Not really. So this is actually the results from just running that like our methods on these images. So we will get like a mean color, the average color out, but you cannot really, and also you have all these like how do you call it, like the floater because of the human occlusion. So again, back to this pipeline. So nerf on the go, we try to handle the dynamic, and then we try to handle the arbitrary length. You can like take many images. But is it possible to, again, enable back the fast rendering? And is it possible to make it like a lighting robust, right? So yeah, again, we have the 3D-GS. It's basically this enable these 4 components. We just try to have like 3D-GS from casually capture images in the wild. So that's basically the thing. We want it should be able to robustly handle arbitrary occlusions, like what we already shown in a nerf on the go. We also want to model any illumination changes, right? And then also we want the real-time rendering. So again, that's basically another follow-up work for the nerf on the go. It's called Wide Gaussians. Yeah. So yeah, it's a work like accepted to NeurIPS. So again, I won't go into detail because it's like sort of similar to nerf on the go in some parts, but this part is actually different, as you can see. So what we do is that first we assign for each of the image a trainable embedding, right? And then we augment each of the Gaussians with another embedding as well, this local primitive like base per Gaussian embedding. And we use a tiny MLP. We take these 2 features as input, and then like we try to produce this like a fine mapping of the base colors to basically apply this affine color transformation. So yeah, we just like try to produce this affine transformation, because it's very simple and it's very we only need very few like number of parameters to produce. And then once you have that, like you can, for each of the thing, you can take the base color and then like apply these affine colors together with it. And finally, we can have the Gaussians with appearance model color rasterized using 3D-GS. And note that like if needed, that we can actually simply bake these final Gaussians into 3D-GS for better like portability and faster runtime. So we don't need to actually keep these whole things together. It's just like once you run it, you can just keep it. And yeah, so you can render this out, and then you can have the loss on that. But then, like on the other hand, you also want to remove the uncertainty, as we said before, right? So again, the pipeline will be, this part will be very similar to nerf on the go. It's like extract the dino feature, get the, again, like it's a fine transformation. We just predict the uncertainty out, and you have the SSIM and the L1 loss, same thing, and you also weighted by the uncertainty as with same thing. Yeah, and to optimize this uncertainty, again, like you just like have the dino from ground truth and the rendered one, and then just like have this like cosine symmetry loss, same as before. So again, like back to these like very complicated cases, if you just compare to the naive or like vanilla 3D I see like, well, we are doing very well. So, yeah, and then what's also cool is that like you can actually do this like rendering on this, again, this fountain, and this is based on methods called K-plane. You can see all this floater. Yeah, it's like it's over blurry. And then if you see here, yeah, well, 3D you cannot really like change the light, like the lighting basically. So we can model this explicitly. And then here's another thing we can compare to like the K-plane. The rendering speed is like ours is real time for such a high res. It's like 800 times 800. And then like the K-plane is actually much slower because it's a nerve-based representation. Here is like last thing I want to show is that it can I just love this interpolation. Give the two images and their corresponding embedding can just like interplay on the embedding, and then you can like on the scenes, like basically disentangle pretty well. Okay, that's basically almost done, but we still have like two missing pieces here. And yeah, well, of course, like everything we have so far, like these like two works I just mentioned, they're from the Go, and then the white Gaussians all require camera poses as input, and they all like not feed forward, right? Again, but then like we should do like one step a time. So one thing we should do is that, well, again, remove the pose requirements. So basically, this means that we have another follow-up work from like the white Gaussians to like WildGS-SLAM. Again, this is a work done by the two amazing students. So also accepted to CVPR. So the key thing here is that, well, compared to the methods from before, now we give this monocular video sequence has like all sort of like people walking around here. We can again try to estimate their uncertainty, and then we can try to output the rendering as here, as you can see here. But at the same time, we should be able to also estimate the camera poses. And this will really make the system very, very cool, because now you really don't need to run like a collab and all that to get the camera poses. And the collab actually not robust at all when you have like a multiple people inside. So yeah, the pipeline is it's straightforward, as you can see here. This part is very similar. Extract the dino feature, get the uncertainty, and oh yeah, wait, see. And then what's the difference part is that, well, now we have an additional like post tracking module, which is very similar. If you look closely, it's very similar to amazing work called WildGS-SLAM. But then like what we do is that we try to modify the WildGS-SLAM by incorporating this uncertainty map. So it's basically, and then incorporate this predicted uncertainty map, and also at the same time we use a depth estimator to produce the metric depth, and we also use the metric depth and uncertainty to guide the basically the dense bundle adjustment here. And yeah, so basically you can use these to really enable accurate camera poses. And yeah, so and then once you have that, you have the keyframe poses already, right? So you can now use these and the depth as well, and you can like get get 3D Gaussians, and you can like unproject the 3D Gaussians using the pose you get and to the scene, and then you can like render the Gaussians through there, and then render the depth out of it, and you have the supervision signal from the rendering and the depth, right? Yeah. So here's basically the basic pipeline. We just want to quickly show some results. Again, this is another scene. It's called like umbrella. Yeah, I find this funny. Like it's a very stage kind of setting, and then yeah. But then like if you look at the comparison to some of the baseline methods, it's really just work significantly better in terms of rendering and all that. Yeah, here's just like a direct comparisons. Yeah, as you can see, you can remove all these artifacts they have. And also the camera pose, the camera pose, if you notice here, actually the camera pose, yeah, the reference is 1:1 truth. Ours is really accurate compared to the baseline. It's just getting worse and worse. Yeah. Here's a real world scenario. So basically, that's the input frame that we have people that walk around in the museum, and yeah. So again, compared to these two baseline, it's just significantly better, and our estimated uncertainty is actually modeling very properly. So now this part we basically already get most part done towards this ideal 3D reconstruction pipeline. So this one missing piece here is the feed forward part, right? So if we are able to enable this part done, that's basically a hope, like one of the hope I have that like this can be achieved very soon. But not yet. So sadly, I don't have this part done. So that's a pity for this talk, but I hope it's fine. But here, for now, I want to give some opinions about the 3D reconstruction. So for example, I indicate here, I think 3D static reconstruction is almost at the last mile. So it's almost solved problem. So for example, this is another amazing work called VGGT. So you can like give like any images, actually not any, sorry, up to like 120 or like 200 images as input. You can have the feed-forward network. Is, for example, in this case, it's like 2 images. You can, again, no overlapping. You can already like get this like beautiful point map as output. And it's actually very cool. And then, for example, like even single image is also able to output such a point map, or it's actually a depth map. Yeah, so same thing like here. It's like it's really interesting that like, well, this kind of work is already able to get such high quality reconstruction, and also this work can also estimate the camera poses. Also, you can even estimate some sort of like a stat like dynamics. And here's another work called MegaSam. Oh, maybe like yeah, stop this. Like the MegaSam is that also you can get like really high quality point map as output, even for like dynamic scenes. You can model explicitly this dynamic objects, and also you can get pretty accurate camera poses, but they cannot really go up to like a really long sequence. So we actually benchmark with our white Gaussian WildGS-SLAM is actually ours could be give like better camera poses. Still, like what I try to say here is that, well, I think 3D static reconstruction is almost at the last mile because of all these like foundation models, like VGGT and all that. But then there's still like many remaining challenges that I want to discuss, and then maybe hopefully can inspire some of you. For example, as I just already mentioned, that it cannot really handle like long sequences like the MegaSam I just mentioned above. And also there's another work called Qt. So it's also, this work is able to handle like all sort of like input. Like could be static, it could be dynamic, could be like unstructured photo collections. However, it's also like passed through a feed-forward network that give the point map as together with the camera poses. However, like this work will just forget everything after like 200 frames or 100 and 200 frames, because they keep this like explicitly keep fixed size of tokens that for specific as a memory, but this won't work. And there are some works that try to solve this problem to extend to longer scenes, but none of them are very accurate. So the camera pose in this case is really awful. Yeah. Another thing, oh, there's apparently there's some here. Again, like I think static reconstruction is almost solved, but the 4D reconstruction is still really hard. For example, as you can see here, at this MegaSam, they can give like this such a point map as output. However, who will use this kind of point map? It's not really useful in my opinion. Why we need such a point map? Or I mean, what we want is actually the able to render like from novel views, right? So apparently, like this is a work. Gaussian flow is one of the work that is try to do this something called like 4D reconstruction, but that's like still of the art method. But look how small the camera can move, and then look at the face, like how blurry the face is, and then how like this different part of the scene has already changed. And this was the state of the art method, and you can see that how hard this problem is, because this is inherently very hard problem. Camera motions, like the scene motions, and maybe like the scene changes and all that, like they are all inherently like ambiguous. So how to disambiguate all these things, it's still like remain as challenge. And as I already mentioned before, right, the feed-forward like pose estimation is not really solved problem. So still, if you want to get accurate camera poses, you still need to have like this bundle adjustment. You need to have like optimization, and that's one of the reasons why, like in the Gaussian WildGS-SLAM, we were still using the dense the DBA, basically dense bundle adjustment, in order to get really good camera poses. And it's also why in MegaSam they were still using that, because, for example, this is a work called AnyCam from CVPR this year again. So they are trying to output, giving the video directly output the camera poses. So they are able to do that. Again, not good. They are like significantly worse than any of the methods here. So how can we really enable this feed-forward posing? Estimation is really interesting. And do we need this like feed-forward pose estimation? Can we incorporate some sort of like online optimization together with the feed-forward pose estimation? Well, that could be an interesting directions. And another thing like I personally interested in is that like how can we actually continuously update your 3D reconstruction? For example, here's a toy example. As imagine that like we can consider changes over time, right? So for example, for a scene like this, if we move the bottle from here to here, and this basically scene has already changed, can you actually do the rendering? Can you like update your scene very efficiently? Yeah, and then also like, for example, here you move the bottle back and then you add another lid here. Can you update again your 3D reconstruction very nicely, very efficiently? And yeah, here's our rendering. So this is also a work from us, but I won't go into details. But it's just like giving ideas. This is just a toy example, but imagine your room, right? So today you update, you put your clothes on your room, but then like the second day you clean your room, and then like you clean your table, and then many things has been removed. Like that's basically, you need a method that is able to continuously update your reconstruction efficiently. Yeah. Another thing I'm personally very, very, very interested in is like, can we actually unify the 3D reconstruction or even SLAM into the LM system? So recently we saw quite some work that basically try to unify the image generation into like the LM system. For example, as you can see here, what they do is that they can extract the text token, they can extract the image token, and they just use the LM to fuse them, and then you do the next token prediction and then you predict the basically the image token, and then you can have VQVAE to decompose to get the image output. And here are some of the images that they generated, and it's actually amazing. And then they also show that by doing that, they can also help some of the VQA tasks, like the understanding tasks for the language model. So it's very naturally to ask yourself, oh, is it possible to? So in the end, like the LM is a very powerful tool. Is it possible to incorporate directly this 3D reconstruction into such a unified system so that like afterwards, imagine you have a bunch of images or videos, just input this to the LM system, then they will give you a 3D dance output, a 3D GS output. You can have a camera poses as output. Yeah, that would be very cool. Oh, what is that? Oh, that's another one has a, yeah. So this is another thing is like what we need to know that like why we need 3D scenes, right? So basically we need 3D, right? We need like 3D representation to be able to really interact with the 3D scenes very quickly at speed. So in this case, like this is a World Labs demo from December last year, and then basically you generate a 3D scenes. Basically, actually, I think they are represent the scene with the Gaussian splatting, and you are able to just walk around inside the scene and then like interact with the scene very efficiently. So this part you cannot use a video model to replace, right? So that's basically one of the thing we need to think about. Okay, if you want to work on 3D reconstruction, if you want to work on like 3D, like research in 3D or graphics, what's the downstream use case here with 3D? I think like interaction, human interaction is one of the biggest bet here. And yeah, but we don't know. Yeah, we will all need to like push forward in this field. Yeah. And that's basically it of the talk. But at the very, very last, I want to show this like one quote from Bill Gates again. This is basically like people overestimate what they can do in 1 year and then underestimate what they can do in 10 years, right? So again, like most of the work was mainly done by the students, but then yeah, still like you can show that, hey, 1 year you can still achieve something, right? But so basically this echo with one of my colleagues, former colleagues, Lars, said like he actually rewrote this quote. It said people overestimate what they can do in 1 week and then underestimate what they can do in 1 year. I really think that's true. So, but maybe you can prove me wrong that maybe you can achieve a lot of things in 1 week. Yeah, that's how, especially with the help with the large language model, right? Yeah. Okay. So that's basically it with the talk today, and hopefully I'm not like really over time and I can have some time for the Q&A. Thank you.
Thank you very much, Songyou. It was really wonderful summary of the line of the work that you are handling. Lots of the challenges in this 3D construction, like handling dynamic objects, like lighting changes, and pose estimation, many things. Yeah, it's very impressive.
Thank you.
We have few minutes to go over with some kind of the questions. So we already have some questions in the Zoom chat. So maybe
okay. Let me check. Yes.
The first,
Harry.
Yeah, 2 questions about the NoPoSplat, the paper.
Mm-hmm. Yeah. What do the VIT encoder and decoder do here? As you can synthesize the obvious given to you with the camera pose with minimal of that. Why can a model infer the scene? Is it possible to train? Yeah. So okay. Well, the key thing here is that we initialize our model, basically this VIT encoder decoder from Duster, right? Or from master specifically. So they were already trained with some sort of like 3D aware information. So they were already able to output basically the point map in the basically in the space. So they are already 3D aware. And what we try to do is that like, well, we just like fine tune this model like with RGB losses, and then this will just enable us to do this like novel synthesis without losing even the ability of well, minimal overlap. Yeah. And what are the universal feature? I don't know what is that universal feature, but yeah. Maybe I can move on to the next question.
It's about dynamic sense.
Yeah, distinction between static and dynamic based on whether there are moving objects within the scene. I see what you mean. Yeah, the precise definition of static. Okay, so the thing is like my definition for that, what's that dynamic is that like well, from first frame to next frame, if you can find the correspondence like very nicely, and then like you can directly use the camera poses and then the intrinsic parameter to project from this first view to the second view perfectly, and nothing changed, that's something static, right? Because you know it doesn't move. But the static is that like, well, imagine you have like a human walking in this scene. So the first frame and the second frame, if you the human in the first frame, but it moved already between the first frame to the second frame. So from the first frame to the second frame, if you just like do the projection from first frame to the second frame, you won't reach to the same point because the human already moved. So that's basically dynamic. Well, I think what's problem remain in 3D static reconstruction? How long do you think it would take them? Well, as I mentioned in some like the challenges and the opportunity part, I think like well, how I still think like how can we get like really robust 3D reconstruction that can handle all sort of like scenarios and get their camera poses out? I think that's like still not resolved. And then also like, can we actually still get like always like a dense reconstruction, for example, like a 3D GS as output rather than like a point map? I think that's still unclear because yeah, it's just hard. Yeah. Yes. Next one, try to adapt feed-forward structure even if you achieve good performance with other structures. Are there any advantages? Yeah, exactly. Though that's a good question. So I mean, you other structure, I guess you mean by, for example, optimization based like NERF or like Gaussian splatting and all that, right? I think one main thing is that all these methods you can definitely do it, but it's just takes longer. And takes much longer to optimize. So for example, like Gaussian splatting is fast to render, but fast to train, to optimize. But still, you need like 10 minutes or like 15 minutes and all that. But like with feed forward, you can, as we showed before, you can get like, for example, in VGGT, even give like 120 images, you can get the reconstruction out after like 4 seconds. And that's actually enable like also some of the things that this can many things, new things you can do with that. Yeah. Oh wow. Okay, there are many more questions. Wait. Uncertainty important. Yes, the uncertainty MLP plays an important role. Yes, it is. It is. Oh no, actually, the MLP is not pre-trained. It's basically rely on the dyno, and then you can jointly train this MLP with a nerve, right? So it's yeah, it's not pre-trained. So it's actually not generalizable. We actually try to have a model that is like generalizable to produce like uncertainty generalizable way, but I realize it's not really robust. And yeah, to use it for
video generated models.
Sorry, which part?
Yeah, the second one was about video generated models, whether the
Oh yes. Some work can perform generally exactly. That is true. Yeah, you are right, very right. Like there's the video generated model. What's the advantage of reconstruction over novice using video generation model? Yes. The thing is like now the video generation model quality is really, really high, right? But I still believe that the actually you can check out a talk from John Barron, recent talk he posted, and then basically one of his points that with video model you need like 5 minutes to generate a two seconds videos or something like that, and then you need like 8 GPUs to do that. But with reconstruction, once you reconstruct the scene, you can just like render this really fast. Like assume you already trained a Gaussian splatting, then you can have the rendering and move around the scene like just like in real time. And the cost is really just very slow, and you don't even need GPU for that. So that's still so that's basically enabled like the interaction part, right? So imagine you have the AR headset, and you don't want to wait every time, move a little bit, and then you have another video model to generate the new scene for that. So I think the 3D is still very essential if you want to achieve like the real-time interaction with the 3D scene. Yeah. Next one, DBA can achieve real-time 4D. Is forward still necessary? What DBA can at least, I mean, it's not really real time in our case. It's near real time. I think it's like, I don't know, 1 or 2 frames per second. So you can still like this part is not fast. The DBA is definitely not real time. The feed forward 4D reconstruction, I think, is still necessary. Real time. Yeah, it is. It's a real time SLAM, but then when you incorporate, you still need to produce. In our case, you still need to estimate the metric depth. You still need to like estimate the this like MLP, like to optimize those things, right? And then you put those into the DBA. So it's still not really real time. And I think the feed-forward 4D reconstruction is just like if you can get completely rid of the need of like optimization for the poses, and also like the 4D scene, basically for the representation. Yeah. Next one, can you briefly share what Google ultimately aim to achieve with 3D reconstruction? Wow, interesting. Well, interesting. I actually don't know. Like, I think Google doesn't care too much of 3D nowadays. For example, okay, what I can share is that, well, definitely there's a whole organization like doing like the AR VR, and that's the org that actually pushing this forward a lot. So and also some of the 3D reconstruction things can be deployed into like Google Maps, right? These immersive views and all that. So if you open your Google Maps, that's already there. And some of the things that you can have like Gaussian splatting actually also in some New York restaurants, and they walk around inside the restaurant. So that's basically the thing. But then I think Google Maps, and then also for the shopping and Google Shopping, and then also Google like the AR VR. I think that's I guess like short-term and long-term applications. And I think also how to incorporate 3D understanding into this large language model like Gemini. That's also, I think, slightly longer term goal, and that's also something that I'm working on. Yeah. And what problems are you currently most interested in? Yeah, I think I think the problem I'm currently interested in is still like, I mean, dynamic reconstruction, definitely one thing, and how can we really get a really robust 3D reconstruction, and how can we actually have a unified model for all these tasks? Like those are the things that currently I'm interested in. Yeah. Wow, another very long question. Let's see.
It's all about yeah, how you handle some multiple issues in one project, and how you make some kind of directions in your project when you have some multiple issues.
Yeah. So that's more like a research question. Okay, yeah, that's a good question. I think it's always like, well, we have a goal. We have a goal that, hey, like we want to achieve something, and then along the way, it's always like you will meet so many different issues, or not as expected, right? So most of my project, none of my projects just like, oh, I have this idea, I try it and then it works out of box. No, never. It never work out of box. It's always like having some issues. And then basically how to resolve those issues, those are the part that is making it very interesting. I think, yeah, that's like part of the research is just, hey, you solve one problem, oh, improves a little bit. However, there's another issue. Let's solve this another issue. Let's solve another issue. And along the way, you might find something very interesting. And then like it could be part of your contribution even. Yeah, I don't know if this resolve your question.
Yeah, lots of questions. Yeah. Actually, we
Yes.
are running out of time, but if I am allowed to ask the last question to you, as you also said, like we are seeing huge advances in just like 1 year. Actually, there have been lots of advances in the 3D reconstruction as well. That means that for many of the people here, especially for the students, uh,
Yeah.
time when they graduate, like after some years, we're gonna also see lots of the changes, right?
No,
We're
I
going
know.
to, yeah, it's kind of crazy time that we are seeing many kind of the new things and the lots of the advances in the many aspects. For in this kind of the situation that we are seeing many fast the advances, do you have
Yeah.
any piece of the advices to the students in terms of how they need to be prepared for those kind of situation, how they need to also build up the some kind of career for especially if they are interested in the 3D reconstruction and the analysis?
Yes, that's a very very tough question to be honest because I if I put myself back to the situation as like you guys, I feel like I would feel so sad. I don't know, like it's moving so fast. And when I was doing my PhD, like the things is not moving as fast, right? Like it's like really like pushing crazy fast. But still, like I mean, what I can give advice I will give also like give like some other people as like similar questions. I think the one piece of advice is like try to find directions that you personally you are interested in, and don't think too much. Oh, this field is like moving so fast and all that, because like no matter how fast the field is moving, if you are interested in this thing and you believe that like this is a fundamental things that like a problem need to be solved, but then like not that many people are solving it, it you just do it, and just try to solve the problem. And if it's a very popular field, yeah, you might have some like collisions to the ideas, but then still like if you are interested in things and you can work on this, like well, it will definitely be different enough. But then if this field is like not a very popular field, but also it's fine, right? If you are interested in something, then for you that's not a work, that's a joy to just work on it, and like, you just enjoy the process. I think the key thing is that, well, figure out something that you are interested and try to enjoy the process. And if you don't know what you want, and like most people they don't really know what they really want, okay, try to talk to your professor, try to talk to your peer, try to talk to other people, and then try to read papers. And then that's how you get inspirations, right? And then that's how you find out, okay, what's the questions are remaining in the field. And then you can think, okay, that's something like an interesting question, but do I have the edge there? Can I actually make a contribution there? For example, okay, global warming is a very tough question, right? But I don't have an edge there. I cannot work on that because I won't make a big difference there. But for example, 3D reconstruction, I can work on that because, okay, I know how to do coding. I learn some computer vision stuff, and I found this interesting. That's why I started working on these things. So I know that like, and also nowadays, with the help of like ChatGPT and all these things, I actually will help you a lot in codings and then finding the right directions. I think just like try to use the tool as much as you can. Yeah,
Yeah.
that's it. I think like, I don't know, like it's a very long and unorganized answer, but that's my thoughts. Yeah.
Yeah, I think that's really great advice. Yeah. Follow your
Yeah.
star. I
Yeah,
think
like the back to just follow your heart and then just do it, enjoy the process. Yeah.
it's tough time, but also it's very exciting time in terms of seeing
Yep.
lots of business. Yeah.
It's
Yeah.
just always like this, right? Getting like harder and harder, but then like also there are always opportunities out there. Yeah. Yeah.
Yeah, I think we are really running out of time, but I guess many people here might also have some more questions. So maybe the people here might be able to contact the Songyou directly by sending email or something in terms of guest
Feel
lecture.
free to send email to me if you have like more questions, and like yeah, if you like unsure about like anything like career wise as well, I mean, let me know. Yeah, I will try to respond. Yeah.
Cool. Yeah.
Cool.
Thank you for the wonderful talk again, Songyou. It was a really great talk.
That's
And
much.
thank you
Yeah,
everyone
thank
for
you,
joining the
Manuel.
today's
Yes,
session. Yeah.
thanks so much for the invite, and then yeah, have
Yeah.
a good day.
Yeah. Thank you. Thank you. Bye. So let me end
Bye.
the session here.
Bye.
Bye.